Right now, even though you can't feel it, everything around you is moving, and not just moving, but spinning. In this video, you're going to discover why rotation appears everywhere in the universe, how gravity turns simple motion into stable orbits, and why planets, stars, and even galaxies circle instead of crashing together. By the end, you'll clearly understand why spinning isn't an accident of nature, but one of the most fundamental behaviors built into the universe itself. And before we begin, make sure you subscribe to the channel and click the bell icon, so you never miss more informative and educational videos like this one. At this very moment, Earth is spinning. It completes one rotation every 24 hours, giving us day and night. That idea feels straightforward, but Earth is doing far more than rotating in place. It is also traveling around the sun, completing one full orbit every year. And the sun itself is not standing still either. The sun moves through space, orbiting the center of our galaxy, the Milky Way. One journey around that galactic center takes roughly 200 million years. Meanwhile, the entire galaxy rotates as well, with hundreds of billions of stars circling together in a vast cosmic system. When astronomers observe other galaxies through telescopes, they notice the same pattern repeating again and again. Most galaxies spin, forming enormous spirals stretching across space. Even here on Earth, rotation keeps appearing. Hurricanes rotate, tornadoes rotate, water spirals as it drains from a sink or bathtub. The same motion shows up everywhere you look. This raises an important question. Why does everything spin? Why is rotation so common across nature and across the universe? Why don't objects simply move in straight lines forever? And if planets orbit stars and moons orbit planets, why doesn't gravity eventually pull everything together into one massive collision? To understand this, begin with something familiar, the moon. Right now, the moon is circling Earth at a speed of about 2,000 miles per hour. It is constantly moving, yet it neither flies away into deep space nor crashes into Earth. If gravity pulls it inward, why doesn't it fall straight down? The answer is that two motions are happening at the same time. First, the moon naturally wants to move in a straight line. That's how motion works when nothing interferes. Second, Earth's gravity pulls the moon toward its center. The moon is therefore falling toward Earth while also moving sideways. These two motions combine to create a curved path. And when the sideways speed is exactly right, that curve becomes a stable circle. An orbit is not a fixed track or invisible ring. It is continuous falling that never reaches the ground. The moon has been falling toward Earth for billions of years, but because it keeps moving sideways, it constantly misses. The same principle explains Earth's motion around the sun. At this very moment, Earth is falling toward the sun due to gravity. But Earth is also moving sideways at about 67,000 miles per hour, bending our path into a curve instead of a collision. But where did this sideways motion come from? Why didn't matter simply collapse straight inward from the start? In the early universe, enormous clouds of gas filled space. These clouds were not still. Motion existed everywhere, slow and disorganized. As gravity pulled this gas inward, tiny amounts of residual rotation remained, and the laws of physics began to amplify it. Like an ice skater pulling their arms in to spin faster, the conservation of angular momentum ensures that as matter moves inward, the spin speeds up automatically. This balance between inward pull and sideways motion produces the stable orbits that have governed our universe for billions of years. The collapsing gas cloud behaves exactly the same way. As gravity pulls the cloud inward, the material becomes more compact. Any tiny rotation the cloud originally had becomes stronger as the cloud shrinks. What began as a barely noticeable drift slowly transforms into a measurable spin. As collapse continues, the rotation accelerates further and further. The cloud spins faster, not because something is actively turning it, but because shrinking while rotating forces the motion to speed up. As the rotation increases, another transformation begins. The cloud no longer collapses evenly in all directions. Instead, it starts to flatten. Material moving along the direction of rotation spreads outward, while gravity continues pulling inward. The result is a shape change. A three-dimensional cloud gradually becomes a thin, rotating disk. A useful comparison is spinning pizza dough. When a chef tosses dough into the air and spins it, the dough spreads outward and becomes flat and circular. The spinning motion pushes material outward along the plane of rotation while compressing it vertically. The same physics applies on a cosmic scale. The collapsing gas cloud flattens into a rotating disk made of gas and dust. This outcome is not rare or accidental. It is inevitable. Whenever gravity pulls together a cloud that has even the tiniest amount of rotation, the result is a spinning disk. Collapse plus rotation always leads to this structure. Everywhere astronomers look, they see the same process repeated. The laws of motion make it unavoidable. At the center of this spinning disk, material continues falling inward. Gas piles up, density increases, and temperatures rise dramatically. As pressure builds, the central region grows hotter and hotter, eventually reaching millions of degrees. At that point, hydrogen atoms begin fusing together. Nuclear fusion ignites, converting hydrogen into helium and releasing enormous amounts of energy. A star is born. And that star is spinning. It cannot avoid spinning because it inherited its motion from the rotating cloud that formed it. Our sun formed this way about 4.5 billion years ago. A massive gas cloud somewhere within the Milky Way began collapsing under gravity. As it shrank, its rotation sped up. The cloud flattened into a disk. The center heated until fusion began and the sun ignited. Even today, the sun continues rotating, completing one rotation roughly every 25 days. But the story does not end when the star forms. The rotating disk surrounding the newborn star does not disappear. Large amounts of gas and dust remain orbiting the star, all moving in circular paths and all traveling in the same direction inherited from the original cloud's rotation. This structure is called a protoplanetary disk, and it is the birthplace of planets. Inside this disk, countless tiny particles move around the young star. Over millions of years, collisions begin to occur. When particles collide gently, they stick together rather than bounce apart. Dust grains attach to other dust grains, forming slightly larger clumps. Those clumps collide with more material, growing slowly but steadily. The process is gradual and patient. Dust becomes pebbles. Pebbles become rocks. Rocks grow into massive boulders. As time continues, these growing bodies attract more material through gravity. Collisions become more frequent. Small objects merge into larger ones. Eventually, mountain-sized bodies form, known as planetesimals. These planetesimals continue colliding and combining, slowly building full-sized planets. The entire process takes millions of years, but the outcome is remarkable. A solar system emerges from what was once a drifting cloud of gas. Here's the critical insight. Every planet was already moving before it became a planet. The material that formed each world was already orbiting the star inside the rotating disk. The sideways motion necessary for orbit was present from the beginning. When particles joined together to form planets, they simply kept the motion they already had. This explains one of the most striking features of our solar system. All 8 planets orbit the Sun in the same direction. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all travel along nearly the same plane and circle the Sun the same way. They did not independently choose this direction. They inherited it. Every planet formed from the same rotating disk, sharing the same original spin. If planets had formed separately from unrelated clouds, their orbits would look chaotic. Some would orbit clockwise, others counterclockwise. Their paths would tilt at random angles. Instead, the solar system looks organized, almost orderly, like grooves on a record spinning smoothly beneath a needle. The reason is simple. All the planets were born together within one flattened rotating disk created by a single collapsing cloud. Even the flatness of planetary orbits comes from this origin. The protoplanetary disk was extremely wide but relatively thin. As a result, their orbits remain nearly flat today. Billions of years later, the structure of the solar system still carries the imprint of its birth. The planets did not only inherit their orbital motion from the rotating disk, they also inherited their spin. Every major planet in our solar system rotates on its own axis. Earth spins once every 24 hours, giving us the familiar cycle of day and night. Mars rotates at nearly the same pace. Jupiter spins incredibly fast, completing a rotation in only about 10 hours, while Saturn follows closely behind at roughly 11 hours. Despite their differences in size and composition, they all share one common feature, rotation, and the reason again traces back to the same fundamental physics. As each planet formed, material from the surrounding disk continued falling onto it. That incoming material was not perfectly balanced. Gas, dust, and rock approached from slightly different angles. Each new piece of material carried a small amount of angular momentum, the tendency to rotate. As more and more mass accumulated, these small contributions added together, creating a net spin. Once rotation began, conservation of angular momentum ensured it would persist. As planets grew larger and more compact, their rotation often increased. Billions of years later, they are still rotating. Moons formed through similar processes. Around large planets, gravity gathered leftover material into smaller rotating disks, miniature versions of the Sun's original protoplanetary disk. Within these disks, particles collided and stuck together, gradually forming moons. Jupiter and Saturn, with their powerful gravity, created many such systems. Today, Jupiter has dozens of moons orbiting it, and Saturn has even more. Each moon moves sideways around its planet, maintaining orbit because it formed within a rotating system. Our own moon likely formed through a different event. A massive object, roughly the size of Mars, collided with the young planet. The impact was violent enough to eject enormous amounts of material. That debris formed a hot glowing disk made of vaporized rock. Over time, the material cooled, collided, and merged together. Eventually, it formed the moon. The moon circles Earth today in the same direction that Earth spins because it formed from Earth's rotating debris. The structure of the solar system still carries the imprint of its birth. Our galaxy, the Milky Way, is a massive rotating disk containing hundreds of billions of stars. It formed from an immense collapsing gas cloud that possessed a tiny initial rotation. As gravity pulled material inward, conservation of angular momentum amplified this spin, flattening the cloud into the disk we see today. Rotation is universal. It prevents matter from collapsing straight into a single point, allowing galaxies, stars, and planets to form. Without this cosmic dance, stable environments where life could develop simply wouldn't exist. Our existence depends on rotation. Now return to the earlier question. If gravity constantly pulls objects together, why don't planets crash into the sun? Why doesn't the moon eventually fall into Earth? The answer again lies in sideways motion, orbital velocity. At this moment, the moon is falling toward Earth under gravity, but it is also moving sideways at roughly 2,000 miles per hour. That sideways motion ensures that as the moon falls, Earth curves away beneath it. The moon keeps missing Earth, continuing its endless fall around the planet. Imagine dropping an object straight downward. It falls directly to the ground because it has no sideways motion. Now imagine throwing that object forward while dropping it. It follows a curved path, moving forward while falling at the same time. Throw it faster and the curve stretches farther. Throw it fast enough and the curve matches Earth's curvature itself. The object never reaches the ground. It falls around Earth. That is an orbit. The moon moves at precisely the speed needed for this balance, maintaining its path without crashing or escaping. The same balance that keeps the moon circling Earth also keeps Earth safely orbiting the sun. Right now, at this very moment, our planet is falling toward the sun under the constant pull of gravity. But Earth is also moving sideways at an extraordinary speed, about 67,000 miles per hour. That sideways motion is exactly fast enough that as gravity pulls us inward, the curved surface of our orbital path keeps bending away beneath us. We continuously miss the sun. Instead of falling into it, we fall around it. If Earth's speed changed even slightly, the outcome would be dramatically different. Slow Earth down, and gravity would begin pulling us closer to the sun. Our orbit would shrink, temperatures would rise. Oceans would eventually evaporate and the planet would spiral inward until it burned up. Speed Earth up too much and we would escape the sun's gravitational hold entirely, drifting outward into deep space where temperatures would plummet. Our current motion represents a precise balance between inward pull and sideways movement, a stable orbit that has lasted for billions of years. This same principle applies everywhere. Every planet, every moon, every artificial satellite remains in orbit, because it is falling inward while moving sideways fast enough to avoid collision. All orbital systems are built on this delicate but stable balance. And remarkably, once established, these orbits can last for incredibly long periods of time. Earth has circled the sun for more than 4 billion years without crashing or flying away. The moon has orbited Earth for nearly as long. Although the moon is slowly drifting away due to tidal interactions, the change is extremely gradual, measured in only a few centimeters per year. For practical purposes, the system is stable. Why are orbits so stable? The answer lies in something space almost completely lacks: friction. On Earth, motion eventually stops because of resistance. Air slows moving objects. Surfaces rub against one another. Energy converts into heat and motion fades away. A rolling ball eventually stops because friction steals its energy. But space is nearly empty, a vacuum with almost nothing to slow objects down. Without air resistance or friction, motion continues indefinitely. Momentum is conserved and energy remains in motion. Once an object begins orbiting, nothing naturally stops it. This explains why the universe is filled with long-lasting motion. Planets continue orbiting. Stars continue rotating. Galaxies continue spinning. Unless a collision or gravitational disturbance interferes, motion persists almost forever. In space, movement is not temporary. It is the natural state. Interestingly, the same principles of rotation appear even here on Earth, especially in weather systems. Hurricanes spin because Earth itself is rotating. Our planet completes one rotation every day, and that rotation means different parts of Earth move at different speeds. At the equator, the surface moves fastest, traveling roughly 1,000 miles per hour due to Earth's spin. Near the poles, the surface moves much more slowly. This difference creates an important effect when air moves across the planet. When air travels from one latitude to another, it carries its original speed with it. But the ground beneath may be rotating faster or slower. This mismatch causes the moving air to curve rather than travel straight. The deflection is known as the Coriolis effect. Because of this effect, large weather systems begin to rotate. In the northern hemisphere, hurricanes spin counterclockwise, while in the southern hemisphere they spin clockwise. A hurricane begins when warm ocean water heats the air above it. The warm air rises, creating an area of low pressure. Surrounding air rushes inward to replace it. As that air flows inward, Earth's rotation causes it to curve, organizing the storm into a spiral. Heat energy continues feeding the system, strengthening the rotation and accelerating the winds. What begins as moving air becomes a massive rotating storm with winds exceeding 100 miles per hour. Tornadoes form through a similar amplification of motion. Powerful thunderstorms create strong updrafts, columns of rapidly rising air. If wind speeds vary with altitude, the rising column begins to rotate horizontally. As the updraft lifts and stretches this rotating air vertically, conservation of angular momentum takes over. Just like the spinning ice skater pulling in their arms, the stretching column spins faster and faster. The result is a tornado, a violently rotating column of air capable of winds exceeding 200 miles per hour. Even something as simple as water draining from a sink reveals the same underlying physics. Any tiny disturbance introduces a slight rotation. As water spirals inward toward the drain, conservation of angular momentum increases the speed of that rotation. The whirlpool strengthens. As the water moves closer to the center, the pattern repeats again. Inward motion amplifies spin. Across every scale, the same rule applies. The universe began with motion, and gravity amplified that motion into organized rotation. Small random movements evolved into structured spinning systems. Gas clouds collapsed into rotating stars. Disks of material formed orbiting planets. Massive clouds formed rotating galaxies. The pattern repeats again and again because the physics never changes. Look upward at the night sky and consider what you are seeing. Every star you observe is rotating. Many of those stars host planets that orbit them. Those stars themselves orbit within spinning galaxies. You are standing on a rotating planet that circles a rotating star inside a rotating galaxy formed from rotating clouds of gas billions of years ago. The chain of motion stretches backward through cosmic history. Rotation is not something constantly forcing objects to spin. Nothing needs to keep pushing. Once motion begins, it continues. Gravity strengthens and organizes it, turning tiny random movements into vast, elegant cosmic structures. Spin is preserved, collapse amplifies rotation, and from that combination, the structured universe we inhabit emerges. When you step back and look at the bigger picture, a remarkable pattern begins to emerge. The same simple rules explain motion at every scale of existence, from a tiny whirlpool in a sink to the rotation of entire galaxies. The universe did not need separate laws for storms, planets, and stars. One set of physical principles repeats endlessly. In the early universe, matter was not perfectly balanced or perfectly still. Tiny differences existed everywhere. Some regions moved slightly faster than others. Some drifted in one direction, while neighboring regions drifted another way. These differences were small, almost insignificant at first, but they mattered. Gravity gathered matter together. As collapse began, those tiny motions were preserved and amplified. What started as random drifting turned into organized rotation. This transformation explains why the universe developed structure instead of remaining a featureless cloud of gas. Without rotation, gravity alone would pull matter straight inward. Gas clouds would collapse into dense spheres with little variation. There would be no flattened disks, no stable orbital systems, and likely no planets. Everything would compress into massive objects. Rotation changes that outcome completely. Sideways motion prevents total collapse, allowing material to spread into disks. In these disks, stars and planets can form. Gravity pulls inward while motion pushes sideways. The competition between these two effects creates balance. Instead of falling directly into the center, material settles into orbit. This balance allows systems to remain stable for extraordinary lengths of time. Solar systems and galaxies all exist because of it. Consider again the moon's orbit around Earth. Gravity pulls it inward, but sideways motion keeps redirecting its path. The moon is always falling, but never arriving. This idea can feel counterintuitive. On Earth, we rarely see motion continue indefinitely. Everything here eventually slows down. A rolling ball stops. Even storms eventually fade. But these changes happen because Earth is filled with friction and resistance. Air molecules collide with moving objects. Surfaces scrape together. Energy converts into heat and disperses. Space is different. Space is almost perfectly empty. There is no air resistance to slow a planet. Once something begins moving through space, nothing naturally stops it. Momentum continues unchanged. This is why orbital systems remain stable for billions of years. The motion established during formation simply continues. The stability of orbits also depends on precise relationships between speed and distance. Each object has a specific velocity. Too slow, and the object spirals inward. Too fast, and it escapes outward. The stable orbit exists between these extremes. Earth occupies exactly such a balance around the sun. Our distance allows liquid water to exist. Temperatures remain moderate, and life can develop over long periods. This stability is not accidental. It arises naturally from gravitational physics combined with inherited motion, a pattern that shapes our entire existence. Even artificial satellites follow the same rules. Rockets accelerate them sideways, and gravity bends their path into a perpetual fall called orbit. Once the correct velocity is reached, gravity turns that motion into a stable orbit. The satellite falls toward Earth but keeps missing. This same rotation explains why systems like galaxies collapse into flat, spiral disks rather than spheres. Rotation organizes motion. Even on Earth, rotation creates the Coriolis effect, shaping global wind patterns and stabilizing our climate. Without planetary spin, our climate would be unrecognizable. Day and night cycles and temperature ranges depend on this motion. From the formation of stars to the spin of black holes, motion guided by physical laws creates structure and order across the cosmos. We exist because of this organized dance, gravity pulling inward while motion carries us sideways, creating the balance and stability that sustains life. When all of these pieces come together, the answer to why everything spins becomes clear. It's not a constant force, but motion that has existed since the very beginning. Gravity didn't create motion out of nothing. It amplified what was already there. Tiny, uneven movements in the early universe were stretched and organized into the systems we see today. When gravity pulled gas clouds inward, sideways movement combined with the inward pull. A small leftover rotation always remained, growing stronger as the cloud collapsed. This rule transformed chaos into structure. Disks formed, stars ignited, and planets assembled. Each level inherited its motion from the one before it, like a physical memory. Objects were never at rest. Sideways motion prevented direct collapse, turning straight paths into stable, curved orbits. Every orbit is a compromise between gravity and momentum. Earth has orbited the Sun for over 4 billion years. These motions continue because space offers almost no resistance. Without friction, energy remains in motion. From the Moon's circle to the Sun's revolution around the Milky Way, momentum is conserved. Once a system starts rotating, it can continue almost indefinitely. Rotation is the universe's way of holding on to its past. It's a legacy of movement that defines the structure of everything we see. This persistence of motion explains why the universe looks dynamic rather than static. Stars rotate, galaxies spin, planetary systems maintain orderly paths. Even black holes often rotate rapidly because they inherit angular momentum from collapsing stars or surrounding matter. The universe remembers its motion. Interestingly, rotation does more than prevent collapse. It creates stability. A rotating system distributes energy and material in ways that allow long-term balance. Planetary orbits avoid chaotic collisions because they settle into predictable paths. Disks spread matter across large areas rather than concentrating everything at a single point. This spreading allows multiple structures to exist simultaneously. Many planets around one star, many stars within one galaxy. Without rotation, gravity would dominate completely. Matter would collapse into dense spherical objects with little separation. Solar systems might never form. Stable planetary surfaces might not exist. Without stable planets, environments capable of supporting life would be extremely unlikely. In a very real sense, rotation creates the conditions necessary for complexity. Even on Earth, our daily experience depends on planetary spin. Earth's rotation moderates temperature differences between day and night. It drives atmospheric circulation, shaping weather and climate patterns. Ocean currents redistribute heat around the globe. Without rotation, one side of Earth could become extremely hot, while the other remained permanently frozen. The balance created by rotation supports stable ecosystems across the planet. The same physical principle also explains why spinning appears naturally whenever motion is concentrated. Consider again a tornado forming inside a thunderstorm. Rising air stretches a rotating column, and conservation of angular momentum increases its speed. The fastest spin emerges not from added energy, but from redistribution of motion. The identical rule applies when a collapsing star forms or when a galaxy condenses from a massive cloud. Across scales differing by billions of times in size, the physics remains unchanged. Even something as ordinary as water draining from a sink reflects the same universal law. Any tiny disturbance introduces rotation. As water moves inward toward the drain, its spin accelerates. What appears to be a small household phenomenon mirrors the processes shaping galaxies. The difference lies only in scale, not in principle. The repetition of this pattern reveals a deep unity in nature. The universe does not require separate explanations for storms, planets, and galaxies. One consistent framework explains them all. Motion persists. Gravity gathers matter. Collapse amplifies rotation. Rotation creates structure. Structure allows stability. When you look up at the night sky, you are witnessing a chain of motion stretching back billions of years. The ground beneath your feet rotates once every day. That rotating planet orbits a rotating star. That star travels within a rotating galaxy. That galaxy formed from rotating clouds born in the early universe. Every level connects to the same origin, motion preserved and amplified over cosmic time. This understanding also changes how we think about stillness. True stillness almost never exists in nature. Even objects that appear motionless participate in larger systems of movement. You may feel stationary standing on Earth, yet you are spinning with the planet, orbiting the sun and traveling through the galaxy simultaneously. Motion is not the exception, it is the rule. So why does everything spin? Because once motion began, nothing stopped it. Gravity gathered matter together, strengthening rotation instead of removing it. Tiny random movements evolved into organized cosmic patterns. What began as subtle drifting became the elegant spirals of galaxies, the steady orbits of planets, and the rhythmic rotation of worlds. From the smallest whirlpool to the largest galaxy, the same story repeats. Spin is conserved, collapse amplifies spin, rotation shapes structure. The universe is not held together by stillness, but by motion, guided by simple physical laws. And the reason planets do not crash, stars do not fall apart, and galaxies maintain their graceful forms is because sideways motion and gravity remain perfectly balanced. You are living inside that balance right now, standing on a spinning world, traveling through space in a vast rotating system that has been in motion for billions of years and will likely continue long after humanity is gone. The universe spins not because something keeps pushing it, but because motion, once created, endures. And from that enduring motion came everything we see, everything we study, and ultimately everything that made our existence possible.